Well, good afternoon. This is 12:30, time for Math 227. Actually 2 minutes late getting started, 3 minutes now. But there was one other student here, but he found out it was L Day and he went down to get some food. So he's coming right back. So hopefully other students will be coming in later. But we'll go on and get started now. I will wait and do the announcements until that student and maybe others come back in. So let's go on and get started at this point. Wait a minute. This is not what I wanted to do. Okay. Minimize that. Okay. This is what I wanted to do from the current slide. Okay. Where we left off last time, we started in we finished 11.6, and then we started in 12.1, and we got the preliminaries done. We got down to example 1, but example 1 isn't given on the slide set, so we're going to do it on example 2, and then we'll come back and do example 2 as well. So let's do example 1. And again, I'll wait to do announcements until anyone else comes in. Okay. It says here, sketching a plane curve. Sketch the plane curve represented by the vector valued function r of t. This is a vector value function. Notice the book and the slide set indicate vectors by bold case. Since I can't write bold, I put the arrow over it. So that's a vector r of t is equal to 2 cosine t I. Okay, and I indicate unit vectors with the caret top rather than an arrow, just so we'll know we're talking about a unit vector, minus 3 sine t j. Now this is a plane curve. It's not in 3 space, it's in the plane curve. And we're only going, t is varying from 0 to 2 pi. So 0 is less than or equal to t is less than or equal to 2 pi, just like the one above. Okay? Now, this is a vector value function. Okay, it says sketch the plane curve represented by that. So let's go on and do our axes, and we will do 1, 2, 3, 1, 2, 3. Okay, 1, 2, 3, 1, 2, 3. Okay, that should cover everything. All right, let's start with t equals 0. When t is equal to 0, cosine is 1. 2 times 1 is 2. So we start right up here. Well, okay, sorry, I shouldn't have done that yet. 2 is the I value, so I did that wrong anyway, so I shouldn't have done it. Okay, 2 is the I value, or the x value. So we're starting here, but let's go on and do the second part. Sine of 0 is 0. So we sure enough are at 2, 0. Okay? Then, man, my eye is itching. I was outside L Day, and I think the pollen got to me. Okay? Then let's go to t equal pi halves. 2 times cosine t. Cosine of pi halves is 0. 2 times 0 is 0. So the I, or the x value is 0, but the y value is minus 3. Okay? Because sine of pi halves is 1. Minus 3 would be a minus down there. Okay? Then, t equal pi, say. Cosine of pi is minus 1. Times 2 would be minus 2, and sine of pi is 0, so that would be 3 times 0. So there we are there. And then we'll go to t is equal to 3 halves pi. Cosine of 3 halves pi is 0, so the x value is 0. The y value, sine of 3 halves pi, is -1. Minus 3 times -1 is +3, so here we are. Okay? So, and then you go around to 2 pi, and 2 pi brings us right back to where we started. Cosine of 2 pi is 1. 2 times 1 is 2. That's the x-coordinate. And sine of 2 pi is 0. 3 times 0 is 0. So the y is 0. So here is our curve. Okay? And I'm not drawing it very well, going to go out on the limb and say this is an ellipse. Okay? And it's going in this direction. Okay? Let me see if I can, whoops, that's not the one I wanted to do. Okay. All right. All right. Okay, that's my best rendition so far of an ellipse. Okay? So that's the shape here, and you see it in the text. That's exactly what you see there as well. Okay. Not too hard to do plane curves. Just two dimensions, because we're in a flat screen, and that's two-dimensional. However, example 2 is going into a space curve. Now, you can also see this at larsoncalculus.com for an interactive version of this type of an example. So let's go to this, and here is example 2. Sketch the space curve represented by the vector value function r of t, again that's a vector function, 4 cosine t I plus 4 cosine tj plus tk, and t going from 0 to 2 pi. So this time we have to do a three-dimensional drawing, and I don't draw 3 dimensions very well, so we'll assume this is an x-axis, this is a y-axis, and this is the z-axis. Okay? Let's start with t equals 0 again. Oh, and let's go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, we might need further than that. Yeah, we will. Maybe. Let me extend z a little higher. Okay. Okay. 5, 6, 7, 8. We might need higher than that, but let's hope not. Okay. Now, when t is equal to 0, cosine is 1. 4 times 1 is 4. So your x-coordinate is 4. Your y-coordinate, t equals 0, sine 0 is 0. So that would be 0 on j, and if t is equal to 0, 0 on k. So your 4 units out here. So here's where we begin. X-axis 4. That is an x there. There's the y, there's a z. Let me move the z just to make it look a little bit better. Okay. This is the z-axis up here. Okay. We'll even draw an arrow. Okay. Now, we'll move next to, I just like the half pi's because they graph better. When t is equal to pi halves, cosine is 0, so you're 0 on x. And sine of pi halves is 1. 4 times 1 is 4. So you're 4 on your j, you're on your y-axis, but you're up pi halves, and pi being 3.14, pi halves would be 1.57. Okay, so 1.57 on z. That's a little over halfway, so we're right about there. So we've come around, and this is hard to visualize in 3 space, but you've left the xy plane and are moving up very slowly until you get to that point. Okay? And what I'm going to do is extend my axes into negative territory because we're going to need them. Okay. Okay, there's x negative. Here's y negative. And here's z negative. We're not going to need z being negative, but I'll put it there just for completeness. Okay? Then let's go to t equal pi. Cosine of pi is -1, so you're -4 on x. 1, 2, 3, 4. You are said that wrong. Yeah, no, I said it right. -4 on x. At pi, sine is 0, and so you're 0 on y, and your pi, which is 3.14 on j. So we're 4 here, and 0 on y, and then you go up 1, 2, 3, and a little bit more. Okay, so you're right about there. So you're continuing to climb upward here, and that's where we are on the, it probably should have a little more curvature in it. I don't draw these things well. So that's the pi, t equal pi. Let's go to t equal 3/2 pi. Okay? Cosine of 3/2 pi is 0, so you're 0 on the x. On the y, you're at -4, because sine of 3/2 pi is -1, so that's -4. And then on k, 3/2 pi would be about something over 4.5. So let's tick off some points here. 1, 2, 3, 4. And go up 1, 2, 3, 4, somewhere about here. Now that's still going up. It just doesn't quite look like it because of our perspective here. Okay? Here you're going above the x-axis, xy plane a little over 3. Here you're going 4.5, but it's really hard to see. Wait, I'm sorry. Yeah, that's right. Okay? Now, then when you get to 2 pi, cosine, of course, is 1, so it's 4 on the x-axis, 0 on the y-axis, but 2 pi, which is 6.28, so you would go up 1, 2, 3, 4, 5, 6, 7, 6. 6.28, about 6 1/4. You're coming around here. Now that's a really lousy rendition, but sure enough, that is. If you imagine a cylinder here, let's put it a different color for that. Say maybe light green, that you have a cylinder that goes through that to that, around to this and this. Here's a cylinder that goes infinitely upward. Okay, this is following a trace along that cylinder as you're going up. Basically, it's a helix is what you call it, as it travels up the outside of the cylinder. Now, my perspective really is rotten, so it's really hard to see, but that's exactly what's happening there. Okay? The cylinder is x squared plus y squared is equal to 16. So radius of 4, going upward from there. Okay. Oh, didn't realize they wanted us to do that. Also, they didn't say to. And I was starting to do it before, and I forgot to do it. How did they get that? Just taking the XY coordinates, which is what I did there when I drew that cylinder there, that would be, let's do what that thing tells us to do. Okay? Okay. Excuse me. A section we skipped was on converting our coordinate spaces, but hopefully you already know this. I hope so anyway. Sorry. if you just took the first two coordinates there, okay, this is a flash either back or into the future or somewhere here. Hopefully you know this, that x is equal to r cosine theta. Okay? Does that ring a bell to you? Since we're using t here, we could call it r cosine t. Okay? Hopefully that rings a bell, because when you get to physics or anywhere else, well, let's just do, in general, your cosine is adjacent over hypotenuse. So r is your hypotenuse, x is your adjacent side, so multiply both sides by hypotenuse, r, and you get x equal r cosine theta. And similarly, y is equal to r sine theta, okay, or sine t, okay. And you get these from your basic trig relationships, that sine of t is opposite over hypotenuse, the opposite side being the y side, hypotenuse being your r, okay. Now, with that in mind, your r in these cases are 4, okay? And what you have is let's see how to say this correctly. So r is 4, so basically you have 4 cosine t is your x and 4 sine t is your y, and you know that sine squared plus cosine squared is equal to 1, so that tells you 4, or if you square this one, you get 16 cosine squared t plus 16 sine squared t let's see, is that quite how I want to do it? Okay, no, that's not quite what I want to do yet. Okay, let me erase this. Okay. Trying not to give things away, but, you know, trying to get you, whoops, I erased too much. If you know that cosine t is equal to x over r, which is x over 16, and sine t is equal to y over, 4, r is 4, okay? Then, what you can say, and that's where you get this then, that x is equal to, well, let's square both of those, okay? So we have cosine squared t is equal to x squared over 16. Sine squared t is equal to y squared over 16, okay? And the sum of these two is equal to 1. Well, the sum of those two is x squared over 16 plus y squared over 16, and we know that has to equal 1. Multiply both sides by 16, and you got x squared plus y squared is equal to 16. So that's where you get your circle from. Okay, that traces a circle on the xy plane, and then from then you just go up the cylinder according to your TK. All right. Now let's go back and do the same thing with example 1, and I think I'll do it here, even though because I've already erased my other thing. Example 1 was 2 cosine ti plus or minus 3 sine tj is equal to r of t. Okay, that was our equation there. Well, doing very similar to what we just did, we say that x is equal to, and this is the x coordinate here, cosine t is equal to x over r, so your x, so to speak, in this case is 2, so cosine t is equal to 2 over r, x over 2, the r is 2, x over 2, and here we have that sine t is equal to y over 3, and if you were to square both of those, you get x squared over 4, and square that, you get y squared over 9, and you do x squared plus y, sine squared plus cosine squared is equal to 1, so that would be x squared over 4 plus y squared, why is this going that? Y squared over 9 is equal to 1, okay? And that's another expression of an ellipse. Now you might say, where did the minus sign go? Well, when you squared your y is minus 3. I probably should have done it that way. Sine of t is equal to y over r, and that basically turns out being a minus y over 9, but when you square it, you get y squared over 9. Okay. Set it backwards. Sine t is y over 3, minus y over 3, but when you square it, you get sine squared is equal to y squared over 9. So that's why you lost that one. And that does give you an ellipse. Okay. Now, as I said before, this maps as an ellipse, as a helix is what you call it. So let me erase my drawing, and then we'll get back to and see how they do it. Okay? From the first two parametric equations, x is equal to 4 cosine t, y is equal to 4 sine t, you can obtain, now this is one way to do it, square x and square y, okay, and you get 16 cosine squared plus 16 sine squared is equal to 1. Okay. Again, I don't like doing it this way. You need to do it as cosine t is x over 4 and sine t is y over 4. Then square both of those. X squared over 16 plus y squared over 16 is equal to 1. Multiply both sides by 16. They kind of skip so many steps, you don't see that coming the way you should. Okay, but anyway, that gives you the xy trace being a circle of radius 4. Okay, this means that the curve lies on a right circular cylinder of radius 4, centered about the z-axis. To locate the curve on the cylinder, you can use the third parameter, z is equal to t, and you just go climb up the helix. The spiral staircase, so to speak. Okay? And here's their rendition, which shows a little bit more of the climb, and that's because they have x and y both coming out of the page at you slightly, and that's why you can see the climb a little bit better. Note that as t increases from 0 to 4 pi, the point x, y, and z spirals up the cylinder to produce a helix. Now, they only asked for us to do it from 0 to... Oh, no! I didn't notice that. Sorry. Oh, wait. Okay. I did what the slide said. In the book, this was a 4T. Okay, not a 2T. On the slide it said 2T, so I did 2T. In the book it's a 4T, and that's what they wanted you to do, and that's what this is showing. You go, the rendition I did just got you around once. Now it's giving you around one more time. So you're directly over this 4 pi later. Okay. So evidently the guy who did the graphics on the slide set messed that up. He put 2 pi rather than 4 pi, and I was doing 2 pi. All right. Now, a real-life example of a helix is shown in the drawing below, and this is in 1953, 2 years after I was born, Francis Crick and James D. Watson discovered the double helix structure of DNA. Now, I've heard and or read, I can't remember which, probably a few years ago, some elaborating stories on how they came about doing this. And they were trying to model this thing and just could not get it to work. They knew it was cyclic, and they just couldn't get it to work until they did a double helix, and then everything fell into place. Okay? So I can't think of much more to say about that. So that's example 2. Let's see if they do example 3. No, they don't. So let's back up and do example 3. Same place we did 1 and 2, we'll do 3. Represent the parabola by a vector value function. Okay? Y is equal to x squared plus 1. Okay? Now, just to give you an idea, you don't have to do it this way, but you can. They drew a graph, and you know what that looks like, hopefully, by now. Okay? This has the vertex is moved up 1 from the origin, and then you go up and out. That's not very symmetric, but you get the general idea. Okay. And it says to represent that by a vector valued function. All right. Here is one way to do it. This is a fairly easy way. Let t equal x. Okay? Let that be your parameter. X equal t, t is equal to x. Then y is equal to x squared, which is t squared, plus 1. Okay? So those are, I've lost one. Oh, okay. Represent the parabola by a vector valued function. Okay? So then the function would be r of t is equal to your x of t, which is a t I plus t squared plus 1 j. Okay? Now, where do we want our t's to range from and to? Okay? Now, they don't say anything specific about this parabola. We'll assume that it's starting at, say, negative infinity. Okay? So let's have t going from negative infinity less than or equal to t is less than or equal to, and how far is it going? I think it's going to have to go to positive infinity. Okay? Now, let's see how that does. If you pick a very large number, and this is a very large number, but larger than I can represent with my graph, that would be negative that would be, let's start with negative 10. So that would be negative 10I plus 101J. That's why I chose negative 10, because I knew it was going to produce a very large J. Well, sure enough, that's something way out here. 10 would be somewhere way out here, and this would be really, really far up, 101J. Then come down from that and go down to, say, negative 1. That'd be negative 1I, negative 1 is your x value, and 2 would be your y value. Negative 1 squared is 1, plus 1 is 2, so negative 1, 2 would also be on this curve. Okay, so negative 1, 101 is somewhere way up there. Negative 1, 2 would be somewhere about here. 0 would be 0j, okay, 0I plus j. And then when t is equal to 1, you'd have your x value would be 1 again, and your y value would be 2 again. And if t is equal to 3, you have 3I plus 10j. So sure enough, that would be somewhere on up there. So sure enough, we do have this vector. And we're producing it in that direction. If you chose the t's to be minus infinity to infinity and chose your position vectors to be those two. All right. Any questions on that? Nobody's in here to ask a question, but I'm just so used to saying that. And they, of course, use ti plus t squared plus 1j. That's usually the simplest thing to do if you have, say, a polynomial or any other type function like that. Have your independent variable be the t, and have the dependent variable be whatever the expression is of t. Okay? Now, okay. Like I said before, I was outside at lunch with L-Day, and I think there's just too much pollen in the air because I'm so clogged up now. I'm surprised you can even hear me. Let's clear this screen. Sorry. And go to example 4. Now, I kept thinking Daniel was going to come back. So far, he hasn't made it. So I'm really tempted to pause it here just so I can go clear my head. So if he does make it back here. Okay. Let's see. He did return. Okay. Did you get something to eat? Yeah. Okay. Is it about over now?
Yeah, they're packing up.
They're packing up, so too late probably to get something to eat. I don't know if you could or not. Yeah. All right. Anyway, we just did example 2 and 3, and what I forgot to show on 3 was the direction it was going, but when I was doing the graphing it, I indicated which points I was doing first. So let's move on to example 4. This is also not in the slide set. We're in chapter 12, which is vector value functions, 12.1 vector value functions. Okay, the name of the chapter is the same as the name of the section that we're in. I'll just turn on the projector, for you. But the others I'm recording, so you'll be able to pick up the earlier part later. Now, here it says, sketch the space curve C represented by the intersection of the semi-ellipsoid, x squared over 12 plus y squared over 24 plus z squared over 4 is equal to 1. Now, on its own, that would be an ellipsoid. Okay, I don't know if you were here probably when we talked about these space curves. Did you follow on the YouTube videos? Okay. If we go back and look at that, what makes this an ellipsoid, if you cover this, that gives you an ellipse. If you cover that, that gives you an ellipse. And if you cover that, that gives you an ellipse. Ellipse in all three dimensions, so you get an ellipse this way, this way, and this way. So this is basically something sort of like a weird-looking football, okay? It's ellipses in every dimension, okay? This axis, the x-axis, that goes to plus or minus root 12, which is something between 3 and 4. This goes to plus or minus root 24. And by the way, that's the same as 2 root 3, plus or minus 2 root 3. This is plus or minus 2 root 6, okay? So that goes almost plus or minus 25, plus or minus 5 on the y, and this goes from plus or minus 2. The square root of these, that would be your z-axis. So it would be a really flat football this way, a moderate football in the x direction, and a pretty long, that would be the main axis in the y direction, okay? So that's an ellipsoid. Now, why do they call it a semi-ellipsoid? Because they say, comma, z is greater than or equal to 0. Okay, now, I don't know if this is helpful or not, but sometimes we refer to this as the origin right over here, and there's your x-axis this way, your y-axis this way, and your z-axis this way. Okay, remember I said we're going between 3 and 4 out on the x-axis, almost 5 out on the y-axis, and just 2 up on the z-axis, okay? So that would be the shape. Now this would just be the first octet here, but it's sort of like an ellipse this way, an ellipse this way, and an ellipse this way as well. What this is saying, you would extend out into the front of the building that way, into the fan room this way, and that way as well, but we're not going down there. So this is just the top half of that weird looking, you might think of it as a puffy cookie, okay? It's just the top half, you're on a flat pan, okay? They show it in the book, but we don't have it on the slide set. So anyway, that's what it looks like. It says, sketch the space curve C represented by the intersection of this semi-ellipsoid, okay, and the parabolic cylinder y is equal to x squared. And they say sketch this, and I really hate that, okay. The parabolic cylinder y is equal to x squared, okay. Now, it says, then find the vector value function to represent that graph. So they say the first thing, let's draw it. So I'm going to do my best, which is not very good, in representing that ellipsoid. This will be my x-axis, this is my y-axis, and this is my z-axis. We're going to do z positive, so the x can go back this way, and the y can go back this way, but z is not going down any. So we're going to stay on this xy plane and above, okay? As I said before, the x is going between 3 and 4, so we'll do it somewhere about, we'll just pick a point there. Y is going almost to 5, so it'll go to there and also back here, almost to there, okay? And then on x, between 3 and 4, 1, 2, 3, 4, so somewhere back around in here, okay? So this will be, and it goes no higher than 2 here, so this will go up like that, this will go up like that, okay, and this will continue around like this will continue around like that, this continues around like that, and then you have the semi-ellipses like this, okay, but also semi-ellipses like this, and that, somewhere back there too. I don't know if that helps, okay? Pretty ugly, isn't it? Don't answer that question. Okay, now we're going to intersect that with the parabolic cylinder, y is equal to x squared. Okay, so just picture the xy plane down here. Forget about z for now. Y is equal to x squared would be 0, 0, 1, 1, minus 1, 1, okay, and 2, 4. 2, 4 would be somewhere here and somewhere there, okay. Now this is just on the xy plane. I've already lost my minus 1, 1. I know I put it there somewhere, but oh, it disappeared. I don't know why it does that. So here is that parabola on the xy plane. Now, how does that trace on this thing? Well, obviously it's right there, okay, because there it does cross. But then it climbs up here to that point and then goes back down that side. So on the x-axis, it's starting somewhere there, and on the xy plane at 1, 2. So let's go out here 1, no 1 this way and 2 that way. Yeah. So it's starting somewhere there and goes up something like that. Oh, no, comes up this way, like this. Okay, that's how it's doing. It goes through this point here, goes up to 2 here, and then back down to a point there. I know that's hard to do, and I wish you had your book so you could look at it there. It's a little bit better rendition, a lot better rendition than what I have. They show the curvature doing something like this. That's extreme. It's something more like that. Okay, so let me get this one off of there, that one off of there. And then over here, it would be doing something fairly similar to it. Yeah, you can't see what it's doing there, so I'll just leave it alone. Okay, something like that. It's going down to touch the point over here, wherever that point is. It's corresponding to this one, and comes up like that. Okay, ugly drawing. Okay, so we want that intersection of this semi-ellipsoid with this. Now, what a parabolic cylinder is picture this parabola and then just go straight up from there. Okay, a cylinder doesn't have to be closed. So this parabola, since we only got half the thing here, it starts at the origin down there and goes around and does it same out that way, like this, around the y-axis here, and then you're going up from there. Just, you know, this curve that comes out here, imagine half a parabola here, and it goes straight up all the way along there. That's what a cylinder is, okay? And that's what it's doing. So now we're trying to describe the intersection of these. Now, drawn all over my writing here, which is not a good thing to do. And here's what I'm going to suggest that you do. All right? It sort of does similar to how we started before, and y'all weren't in here when I did the example 3. But since we know the least about the x, and a little bit more about the y, and we can come up with something about the z, then let's start and let your parameter t equal x. Okay? Now, we know from this expression that then, since y is equal to x squared, y is equal to t squared. That's got to be true, right? from right here. That has to be on the curve, okay? And here we can solve this and do, what I'm going to do is multiply everything by 4, okay? And that will give me x squared over 3 plus y squared over 6 plus z squared is equal to 4, right? Multiplying everything on both sides of this equation by 4. In other words, I'm isolating the z squared. Okay? Now I'm going to subtract these from the other side and have that z squared is equal to 4 minus x squared over 3 minus y squared over 6. Okay? Now, z is equal to the square root of that. And it's only the positive square root, because you see z is always positive. So I don't have to do plus or minus, just the positive side because of this, just the positive side. So z is equal to the square root. Oh, here he is. Vince is here. And before I forget it. Yeah. Oh, even swap. Okay. Okay. Now, since we've got a crowd here, and I forgot to tell y'all when you came in, because you come in at different times, but let me go and say it now. I also record it while people are listening to it, hopefully. They told us this very early in the term, like back in January. And then I think I put a mental block out there so I would forget it if at all possible. And someone reminded me this morning. This is bad news, Bears. Next Wednesday, someone in the Chancellor's office is requiring that the entire instructional faculty go down to Montgomery next Wednesday, 1 week from today. Yeah, they're going to bus us down there. We're going to be in meetings all day and bus us back. It is a waste of time, a waste of effort, a waste of money, a waste of everything, but we're required to do it. So next Wednesday, I will not be here. So we will not have this class. Now that's not saying that you want that the school's closed on Wednesday. If you have another class on Wednesday that's being taught by an adjunct instructor, those classes are going to continue. The whole staff will be here, everyone here except the full-time instructors. We'll all be down in Montgomery. Yeah. Yeah, Dr. Bryant will be here. Yeah, he's not going to Montgomery. Okay, so if you're in the physics class, he will be here, but this class will not meet. Sorry about that. Now, if you want me to, I can maybe record something and have it out there for you. Is that something you would like me to do?
Yeah, if you can.
Yeah, if I can. Thank you very much. Okay. Huh?
I said if not, I ain't gonna hold the issue.
Okay. Well, what I'll do, I'll look, and I do have recordings from the last time I taught this class. It may not start at exactly the same point or end where I would have, but that'll be the best thing. So we'll do that, and I'll pick up from wherever that one leaves off and continue. Okay. So we'll talk about this again on Monday. So I'll leave that recording there. Now, the old recordings are at the top of the list, the playlist on YouTube. The new things are at the bottom. So you'll see what we've done since the beginning of the term at the bottom, and then at the top will be this part. So where we leave off next Monday, then go to the top, find that, and then after that, go back to the bottom again. Okay, what we're doing is this. This is example 4 on page 822. Okay, section 12.1. Okay, so what we have here, we just solved this for z squared, now taking the square root, but only taking the positive square root because z is always greater than or equal to 0. You have the square root of 4 minus x squared over 3 minus y squared over 6. Okay, but we know what x is. X is t. Okay. So this z will then be the square root of 4 minus t squared over 3 minus, I don't know why I put a vertical line there, okay, minus, we also know what y is. Y is equal to t squared. So this will be t to the 4th over 6. Okay, that's what your z is. Okay. So we have just come up with, why did I do that? I'm not sure. We've sketched it. That's all it asked for. Oh, then it says, then find the vector value function to represent the graph. So what would that vector value function be? It would be r of t, just like this, r of t, and since I can't draw right in bold, I use the arrow. R of t is equal to, your x is ti, where is it? There it is. Yeah, ti plus t squared j, that's the y, plus the square root of 4 minus t squared over 3 minus t 4th over 6 k. I'm sorry, I already used, okay. Now, that's one, okay? It's not a very good one, but it is certainly one, okay? Now, finding the limits of that might be yet another issue. X is going from, we have to find the point of intersection of these, okay? That will be where z is equal to 0, and this is true. That would be the furthest out x in negative and positive directions. So let's see if we can figure out what that's going to, from and to. And x is also, all right, let's do sort of the same thing we just did before. Let's back it up until this thing is 0. And what value for t would that be 0? Yeah. Now, they do another thing here, which is a good idea. This is really messy, isn't it? Okay, this expression for z here. So let's see if we can clean that up a little bit. Least common denominator in there is 6. So to get the 4 to become with a denominator of 6, that would have to be 24 minus 2t squared minus t to the 4th over 6. That gives us the same thing as this. What's inside the radical down here is that, okay? We just put everything over 6, that would make 24 minus 2t squared minus t to the 4th, okay? Now, that starts when z is equal to 0. So let's see if we can clean this up a little bit by factoring, okay? And this will be, I'm pretty sure that's going to be 6 minus, no, 6 plus t squared here, and 6, no, and 4 minus t squared there. Okay, let me check on this. Nope, yep, I think I got it right. Over 6. Let's see if that's right. 6, okay, if you multiply that out, it'll be 24 minus 6t squared plus 4t squared, that would be minus 2t squared minus t to the 4th. Yes, that works. Okay? Now, where is that equal to 0? Because that needs to be 0 for z to be 0. Well, 6 plus t squared is never 0. Ever. Okay, not in the real number system. That's where we are. But 4 minus t squared is 0 at t equal minus 2 to plus 2. Okay? So my drawing really isn't too far off. It is. Okay? So it's minus 2 to the plus 2. So, I don't mind leaving it like this, but that just lets you know minus 2 is less than or equal to t is less than or equal to plus 2. Now this time I will draw the arrow. This curve is going like this. Okay? It starts over there, comes up, around, and down. All right. They just rewrite what I wrote in fractional form. They wrote it actually that way. And that was the k. Which is, it's the square root of that. Okay, let me put that in there. The square root of that. That would be the k value. Let me see if that is indeed what they did. Yeah, square root of 6 plus t squared times 4 minus t squared over 6 times k. T going from minus 2 to 2. Okay. Just a little bit longer way of writing it, but it certainly looks a little nicer too. Okay? And it lets you see where your zeros are. Whew, goodness gracious. This is why we did quadratic surfaces at the end of chapter 11. So we could do this. So let's move on to, any questions on this? I know it's a lot of hocus pocus here. So let's move on to limits and continuity. All right? Now there's some verbiage at the top of the page, and basically that's telling you that to add two vector value functions, you add each component separately, okay? That's all it's meaning, okay? If R1 is f of ti plus g of t, j, and R2 is f2 of ti plus g2 of t, j, add the i's, add the j's. That's how you add vectors. If in 3 dimensions, you just do it in all 3 dimensions, okay? Subtracting, same thing, okay? Multiplying by a constant, same thing, okay? Dividing by a non-zero constant, same thing. All right. Pardon me? Huh? All right, thank you. And by the way, Catherine? Yes. Next Wednesday, we are required, the full-time faculty are required to go down to Montgomery for a meaningless meeting, but so there will be no class next Wednesday. I will leave what we would have covered up on Blackboard, but it'll be what I recorded last time I taught this course over approximately the same sections. But we'll be here Monday, and I'll let you know where to look on Blackboard. Okay. All righty. Okay. I'm sorry? Okay, test 2? Okay. Let me get that for you. And I forgot to bring my watch in, so y'all let me know when it gets close to time, okay? How are we doing?
We did 136.
Huh?
We got like 40 more minutes.
40 more minutes. Okay, good. Okay. 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 I'm getting warmer. There we go. Okay, now wait a minute. What she just turned in was find the indefinite integral. Did you get that one? Or is it just this last one?
Yes, test 2.
Huh?
It's test 2.
Test.
Test 2.
Test 2. Okay. I think this is the one. Okay, this is the one I passed out right before spring break. That's the one you need. Okay. Oh, I got the previous one in there? I did. Make sure I did. Yes, I did. Right. I just saw it. It was stuck together. Okay. Okay. So let me go back, and before we get here, let me do it here. If you're, and hopefully this is just what you would expect. If you're adding two vector value functions, R1 of t plus R2 of t, where R1 of t is F1 of t. Now, R is a vector value function, F is not. Okay, I'm just doing these in 2 dimensions. This is R1 of t, here's R2 of t. F2 of t I plus G2 of I, G2 of t j. Okay, that is your R2. Here's your R1. Okay, to add those together, that would be F1 of t plus F2 of t I, add the I components together, and then plus G2 of t plus G1 of t plus G2 of t j. Okay, just add the components. Okay, if you're subtracting, you just subtract. Okay, well, I'm sorry. Wait. The plus is there. This becomes the minus, and that becomes the minus. Yeah. You keep you still add the components just like you normally do, but you subtract the components of the two vectors. Okay? Now, if you got C times R of t, okay, that would be, and your R of t is just, forget the ones there, just like before, that would be C times F1 of ti plus G1 of tj. Okay? Now, for those who aren't familiar with my notation, the book bolds the vectors. I put arrows over normal vectors. I put house tops over unit vectors. So when you see me write that, that indicates that's a unit vector. Just to remind you, this is just any old vector. It doesn't have to be a unit vector. Okay? Which this, of course, is then just C F1 of ti plus C G1 of tj. Or I guess they're just calling them, they still keep the ones in there. I'm not sure why. Okay? If you're dividing a vector by a non-zero constant, okay, we don't usually do this one, but they're doing it here. That would be just 1 over C times F1 of ti plus G1 of tj, which would be F1 of t over C I plus G1 of t over Cj. Okay. They felt like they needed to say that, so it's said. So, let's now move to the definitions of the limit of a vector valued function. If R, bold R, I would put an arrow over it, is a vector value function such that R of t is equal to F of ti plus G of tj. Remind me, this is a vector value function. Notice the bold R. These are scalar functions of t. No vectors included here. They're just the components of your I and j vectors of your R vector R. Okay. So if that's a vector value function such that f of R is equal to f of ti and g of tj, then the limit as t approaches a of R of t would be the limit as t approaches a of f of ti plus the limit of t approaches a of g of tj. So this would just be basically f of a I plus f g of a j. Okay, provided that f and g both have limits. If they don't, it doesn't have a limit. Okay, in space you just do all three vectors there. The limit of R of t, if this is a spatial vector, a three-dimensional vector, t approaches a would be the limit of t approaches a of f of t I plus the limit of t approaches a of g of t j plus the limit of t approaches a of h of t k. Okay, provided that f, g, and h all have limits as t approaches a. If they don't, there is no limit for the vector value function at all. Okay. Now, as R of t approaches a vector L, if R of t approaches a vector L, here's a vector L here. If R of t is swinging around this curve, it's pretty long here, getting shorter as it goes up here, and happens to do there, at least it looks like it's getting shorter. As that approaches the vector L, as t approaches A, the length of the vector R of t minus L approaches 0. The difference between these approaches here. See, here's R of t, here's L. The difference between R of t and L, that would be the same as R of t minus L. So R of t would be here, minus L would be then down this way. And that would be a vector that would go from plus or negative t. Here, that vector, as these get closer together, that difference goes to 0. This is that vector, R of t minus L. Okay? From right here, that would be in this direction. In this direction, plus a negative L. So you take the negative L, put it in here, and put it down here. Yeah. Negative L would be in that direction, but at the end of this one, this would be the vector R of t plus a negative L. Translate this up to here, and you've got exactly that. So as this thing swings around and gets closer to L, this difference is going to 0. Okay? So that the magnitude of R of t minus L is approaching 0 as t approaches A. And that's illustrated graphically here. Here's the first difference function. There's the second one, there's the third, the fourth, the fifth, until finally going to 0. As t approaches A, then R of t is approaching the limit L. And for the limit L to exist, it is not necessary that R of A be defined or that R of A is equal to L, which is interesting. I just sort of said it was, but it's not required that to be. Okay? Interesting. Okay. The next definition extends the notion of continuity to vector value functions. This is on the top of your page 824. Okay. A vector value function R is continuous at a point given by t is equal to A when the limit of R of t exists as t approaches A. So the vector value function is continuous at the point given by t is equal to A when the limit of R of t exists as t approaches A. Okay? So the limit of R of t as t approaches A would then be R of A. Okay? Exactly, I hope, what you expect it to be. That's what I would say. a vector value function R is continuous on an interval I when it is continuous at every point on the interval. Now, usually when you say an interval I, you usually don't count the endpoints. You could, but most of the time we don't, okay? Now, discuss the continuity of the vector value function, this one. R of t is equal to ti plus aj plus a squared minus t squared k, where a is some constant, okay, at t is equal to 0. Discuss the continuity of that vector at t is equal to 0. If t is equal to 0, this is obviously 0i, right? This is aj. A is some constant, so you've got some j dimension there. This one would be a squared k, as t at t is equal to 0. Now, is that continuous? Okay? At that point. I see no reason for it not to be. Oh, I'm sorry. No. I see no reason for it not to be. That would just be some point on the the YZ plane. X has a 0 value there, so you're on the YZ plane. That would be this plane here, and you would be a in the y direction and a squared in the z direction, whatever the value a is. Now, what if a was equal to 0? Then it would be the origin, okay? Because 0i plus 0j plus 0k, that would be the origin. I think that would be okay too. I don't see any problem with that. But I think it would be all right. Let's see what they say. As t approaches 0, the limit is, like we just said, 0i plus aj plus a squared k. Okay? See no problem with that at all. Okay? When a is equal to 0, that is the origin. When a is any other value, that's some point out there, be fine. aj plus a squared k. Because r of 0 is equal to that, you can conclude that r is continuous at t is equal to 0. Yep, no problem there. Even if a is equal to 0, still continuous at the origin. Okay. By similar reason, you can conclude that the vector value function r is continued at all real numbered values of t. No reason for it not to be. Okay? Now, for each value of a, the curve represents the vector value function in example 5. Okay. I'm trying to. Okay. Looks like the same function, doesn't it? For each value a, the curve represented by the vector value function in example 5, which we haven't done, I don't guess. That wasn't 5, was it? Oh, it was. Okay, yeah. Okay. We just finished 5. That was 5. I didn't notice that. Is a parabola. Okay? For each value of a, this is a parabola. Okay? Because this, what it means for it to be aj, okay, that means you only have one value on the y-axis. Okay? A, whatever that is. If it's 0, it's 0. Okay? If it's 7, it's 7. Minus 4 is minus 4. And then you have a function that's ti, so x is equal to t, and this is equal to the z is equal to a squared minus t squared. Well, x is equal to z is equal to a squared minus t squared. That's a parabola. That is a parabola. Okay, and this is what it looks like. And when A is equal to 0, you've just got that right there. You would have T, and this would be T squared, minus T squared. Yeah, if A was equal to 0. So that would be X equal, or Z is equal to minus X squared. Ah, here it is. I was trying to see it on here. See, it's a parabola going down like this. Don't get this confusion. It's the parabola doing like this, okay? And then anywhere else, for any value of y equal a, then you have parabolas that do this, okay? That's your shape here. You can't see it very well here. There's that parabola, here's this parabola, here's that parabola, here's this parabola, here's that parabola. They all arch above the y-axis because y is a constant. For whichever a you choose, these are the parabolas you get. Larger and larger a's, you get higher and higher values here, okay? But you get further and further away from your the origin on the y-axis. Okay. Now, oh, and you put them all together, and you get the hyperbolic paraboloid, this one right here. Y squared minus x squared is equal to z. Where do you get that? Well, y is a, so there's your y squared minus x squared. T is your x squared. That's equal to z. And that, sure enough, is that paraboloid you see there. Remember, a paraboloid is a lot like a saddle. I wouldn't want to sit on that saddle. That's a pretty uncomfortable looking saddle. But the horse would be along the y-axis and your legs would be across here. The saddle just goes awfully far up and down in front of you. That would be a pretty stupid saddle. But anyway, that's your hyperbolic paraboloid. Paraboloid, because one variable is first to the first power, the other two to the second. Hyperbolic, because when z is constant, that's a hyperbola. Okay? That is your equation of hyperbola. And one is positive, the other is negative. Okay. That was example 5 in the continuity of 5. Now let's go back and do example 6. Oops, don't use that. Okay. Determine the intervals on which the vector value function r of t is equal to ti. Is this looking familiar? Oh, different one. Plus the square root of t plus 1 j. Okay, be very careful when you are doing these. If you have a radical there, you end the radical before you put your unit vector, plus t squared plus 1 k. Okay? What it says here is determine the interval or intervals on which this vector value function is continuous. Any problem here? Your f function here, the x function is t, continuous everywhere, no sweat there. The z, continuous everywhere, no sweat there. However, the j, the y value here, problem. What's your problem? What's the issue here on the domain of t? Okay, what's inside the radical cannot be negative. So another way of saying that is that t plus 1 is greater than or equal to 0. It cannot be negative. It has to be positive, or non-zero, anyway. No, I mean non-negative. Yeah, which could include 0. Well, if you subtract 1 from both sides, you get t is greater than or equal to -1. Well, if it is on any single part, it's that on the whole part. And here's Charles here. Okay, and let me make my announcement one more time. Every time someone else comes in, I've been saying this, so people listening at home, you'll have heard it many times. Somebody in the chancellor's office has required that all the full-time instructors, I guess at all the community colleges, at some time or another, go to Montgomery. And I think there's 2 different groups, and we're in the group that goes next Wednesday. So next Wednesday, I will not be on campus all day long, okay? I'll board a bus sometime early Wednesday morning and get back sometime late Wednesday evening. We're the whole full-time faculty. Now, if you have any other courses taught by adjuncts, like Dr. Bryant or something like that, yeah, those classes are still going to happen. This class will not happen. So what I'll do, and I'll tell you this at the end of class on Monday, I'll point out to you what to look at on YouTube videos to cover the next class, okay? And then we'll pick up wherever that video ends, and that's where we'll pick up the following Monday. We just don't have a lot of term left, and y'all said you wanted something to watch, so I'm giving you that to watch, okay? Believe me, someone said that, so I said, sure, we'll do that. All right, so if t is restricted to be greater than -1 here, it's got to be greater than -1 there, and got to be greater than -1 there. So that's going to restrict this, for this to be continuous. So the component functions are this. Both f and h are continuous everywhere. The function g, however, is continuous only from -1, t greater than or equal to -1. So r is continuous on the interval, and you can write it as an interval from -1 to infinity. Okay, positive infinity. That's the other way to write it. That says the same thing. They just wrote it that way. All right, enough of 12.1. All right, homework exercises, any of the odds, 3 through 9, they're all at Calc Chat. 3 is at Calc View. Do number 11, it's at both Calc Chat and Calc View. Do either 13 or 15 or both, they're at Calc Chat. Do 17, it's at Calc Chat. Do either 19 or 21 or both, they're both at Calc Chat. Do any of the odds 23 to 29, they're all at Calc Chat. 25 is at Calc View. Do any of the odds 31 to 37, they're all at Calc Chat. 31 is at Calc View. Do 39, it's a Calc Chat. Do 41, it's a Calc Chat. Do either 43 or 45 or both, they're at Calc Chat. Any of the odds 47 to 53, they're all at Calc Chat. 51's at Calc View. Any of the odds 55 to 61, they're all at Calc Chat. 55's at Calc View. Try doing 63, it's at Calc Chat. Any of the odds 65 to 69, they're all at Calc Chat. 67's at Calc View. And then do any of the odds 71 to 75, they're all at Calc Chat. And you can consider or think about doing 77 and or 79. They're not required. That's just exploring some concepts there, but you can look at them if you'd like. 81's one that you can probably do. It should be at Calc Chat. And 79 and 77, 79 may be at Calc Chat as well, so you can look at that, at least read what they say. 83's a proof, 85's a proof. You can do either or neither if you'd like. They should be at Calc Chat as well. You can think about 87 if you'd like. It should be at Calc Chat. And there's a particle motion problem, 89, that you can probably do at Calc Chat. Now, there is a little section project that we're not going to do called The Witch of Agnesy, which is a terrible strange happening. I can't think of her first name, but there was one really Maria, I think it was, very famous female mathematician back in antiquity. I think this was back BC type era, okay? Believe she was Greek, though her name sounds more Italian. I don't know what her origin was. but she was a brilliant mathematician. Most of the time, women didn't even get to study mathematics. I think her father was a mathematician. He taught her. She was excellent. And she was well known, well respected. And she came up, developed this curve, has a very special thing, and they named it something. But when it got translated from whatever that language was to whatever the next language was, they mistranslated it. And it was something else, and the translation got witch. That wasn't originally witch, but it's just not surprising to me that male misogyny, or whatever you would call it, was still in effect back then, and since she came up with it, they called it the Witch of Agnesy, even though that wasn't the original name. It's continued through time as known as that. The reason I go into that is saying it has nothing to do with the witch. It has nothing to do with anything that just got the name. But she would be an interesting paper topic. Hint, hint, okay? Because in this, one of my best classes ever, of course, I only have two due papers in so far. So please don't forget you have a paper due before the end of the term. And while we're on the subject, I've only received 3 of your test 1s. So please, folks, get me test 1 in. Test 2, y'all got right before the break. Did everybody get one? I know I gave 1 today. Okay. And you just turned that one in. Very good. All right. All right. So that was the Witch of Agnesy, okay, which is a very terrible accident of a translation. All right. Now we're through with section 12.1. So let me end this, discard that, and we have about 6 minutes left, right? All right, let's see what we can get done in 6 minutes. 12.2. But remember, we do have class next Monday. It's just next Wednesday we do not. Okay. We'll go from current slide. And 12.2 is differentiation and integration of vectored value functions. And we'll differentiate vector value functions and we'll integrate vector value functions. And in so doing, hopefully you'll see that there's nothing very new here. Okay, differentiation of vector value functions. However, they're going to drag it out as much as they possibly can. So let's see what happens. The definition of derivative of a vector value function parallels the definition of a real value function. And technically, the real value function was this definition. The derivative is a limit as, if this was an f prime here, of f of t plus delta t minus f of t divided by delta t. The limit that delta t goes to 0. Well, now, rather than it being a scalar function, it's a vector function. So it's still the same thing. The derivative of a vector value function, r of t, is the limit as delta t approaches 0 of r of t plus delta t, that's some difference in space, minus r of t, and that difference divided by delta t. For all values t for which the limit exists. Okay? If r prime does exist, then r is said to be differentiable at the point t. Okay? If r prime exists for all t in an open interval, as I said, usually our intervals are open intervals I, then r is differentiable on the interval I. Differentiability of vector value functions can be extended to closed intervals by considering the one-sided limit. And if the limit, as t is approaching the outer or the first value, first or last value, if both of those limits exist, then you can count differentiability on a closed interval. All right, so differentiation of vector value functions can be done on a component by component basis. Here's the key, folks. Write it down in component form, take the derivative of each of your components. To see why this is true, consider the function r of t is equal to f of ti plus g of tj. Okay? Where r is a vector value function, f and g are scalar functions. Okay? By applying the definition of derivative produces the following. Now, if you go in gory detail here, the R of t, that's R of t. R prime of t would be the limit as delta t approaches 0 of R of t plus delta t minus R of t over delta t. That's our definition. What would that be if you wrote them out? This would be f of t plus delta ti plus g of t plus delta tj minus f of ti minus g of tj. Okay? Then bring this one and this one together with the i's, these two together with the j's, and here you have, as long as f and g are both differentiable, that was required here somewhere, but if this is differentiable, that's f of ti, f prime of ti. If this is differentiable, that's g prime of tj. You got it. You just differentiate by component, component by component. And this extends to 3, 4, or 17 dimensions. We're going to stick with 2 and 3, okay? This important result is listed in the theorem shown below. If R of t is equal to f of ti plus g of tj, where, I don't know what that vertical line is, but it's in there. F and g are both differentiable functions of t. They are scalar functions, differentiable scalar functions of t. Then R prime of t is just f prime of ti plus g prime of tj. You can't get much simpler than that. Just differentiate each of your components. If R of t is equal to f of ti and g of tj plus h of tk, 3 dimensions, where f, g, and h are all differentiable functions, then R prime of t is f prime I plus g prime j plus h prime t. Just take the derivatives of each component as you go. Now, note that the derivative of a vector value function R is in itself a vector valued function because it's still got the I, J, and K. You can see from figure 12A here, that R prime of t is a vector tangent to the curve given by R of t, pointing in the direction of increasing t values. So here's your curve, R of t. Okay? That's the curve represented by R of t. R prime of t, and what they don't tell you here is R is increasing from here to there, as t is increasing from here to there. Because when right here, R prime of t is in that direction of the increase, okay? Now, if you went a little bit further, this would be R of t plus delta t, okay? So this difference here divided by your delta t would be the derivative, and that's basically what that is. Now, well, the limit as delta t is approaching 0. This is sort of a secant function, not quite the same direction here, but the smaller you get here, as the delta t gets less and less and less, this is indeed pointing in that direction. You get closer and closer to that direction, that's your R prime of t. Okay. Do we have time for example 1? We do not. Is it 1:10 already? Okay, shucks. All right, we will start with example 10 on Monday. Remember, we do have example 1 on Monday. Remember, we do have class on Monday. I will not be here on Wednesday. So you can come if you'd like, work among yourselves, watch the video, whatever you choose to do. Okay? If you have other classes that are taught by adjuncts, those classes will meet. Full-time instructors, check with your instructor to see if that instructor is also required to go to Montgomery. I think they are, but someone might be able to talk his way out of it. If so, I'd like to know how, okay? But I don't think that's going to happen. All right, I don't think we got far enough for any new homework exercises, but you got them from 12:1. Good deal. Thank you so much.
I did my best on
Okay.
test 2.
All right. Okay, good deal. Okay. All right, we'll pick up and go from there on Monday.